This section is all about our particular perspective, also known as our frame of reference. So you made a map and you fixed a direction on it, and now north on your map is not the same as true north. Does it matter? It turns out that it doesn't matter what direction you pick north to be on your map from your frame of reference. If you need to use someone else's map with a different north, you can transform between the two by rotating one map so that your north points the same way as their north. If you have different origins too, then that isn't a problem either. You can transform from one system of coordinates to the other by adding on the relative displacement between your respective origins. So what is true north anyway? And why have different orientations and origins? True north is the direction along the Earth's surface towards the geographic North Pole. This is different to magnetic north, which is the direction that a compass points towards magnetic north. It is also different to grid north, which is the direction northwards on a map projection. True north and grid north are slightly different because a map is a 2D flat representation of the Earth's curved surface. The lines parallel to the y-axis, the lines of longitude, are parallel on a map but get closer together on a curved surface, meeting at the North Pole. So why do we have different origins and orientations? For convenience. We use whichever is most convenient for working in our frame of reference. For example, Ordnance Survey maps of the UK have their origin in the Atlantic Ocean, meaning that the UK is in the positive quarter of the XY plane. So why else do we care about reference frames? Well, they also determine whether the laws of physics work or not. We can transfer between what we call inertial reference frames and know that the same physics applies. We can have a different perspective, look at things from a different angle or from a different place, and know that if we did an experiment, like throwing a ball into the air and catching it, the result will be the same, whatever our reference frame. It turns out that if we are moving at a constant velocity, then we are in an inertial reference frame. For example, if you play catch on a train moving at 100 miles per hour in a straight line, you'll have the same experience, that is, the ball will do the same thing, as if you were standing playing the same game of catch in one of the fields rushing by the window. This is the reason why you don't feel speed. What you do feel, however, is acceleration. Newton's second law, force equals mass times acceleration, tells us that. As soon as you find yourself in a non-inertial reference frame, the laws of physics don't work. From your perspective anyway. For example, try playing catch whilst going around on a children's roundabout. The ball veers off to one side, disobeying the laws of physics, but only from your non-inertial, accelerating round in a circle point of view. To your friends standing beside the roundabout, the ball travels straight because they are observing from an inertial reference frame. But hang on a minute, we're on the Earth, a ball spinning on its axis at 1 revolution per day and orbiting the sun once a year. There's definitely circular motion going on here, therefore acceleration. So are we in an inertial reference frame or not? Well, no, we're not. But luckily for us, the accelerations involved are usually small enough to make little difference to the accuracy of the results calculated, if we assume an inertial reference frame. Unless we're doing something on a large scale, like firing a gun a really long way, where the bullet will be deflected to the right in the northern hemisphere or to the left in the southern hemisphere. The laws of physics are the same in all inertial reference frames.